Suresh Gupta? Is Suresh Gupta available? Suresh Gupta? Hello? Suresh Gupta, is it audible?
Yes, sir. Audible, sir.
Okay, Suresh Gupta. Okay. Thank you, Ajay. Suresh Gupta? Ajay, whether Suresh Gupta belongs to global positioning system?
I'm checking, sir. 1 second.
Yeah. That's what I'm asking.
Okay. In WhatsApp group, he was not there, sir.
But ac- actually, it doesn't
Act-
belong to global positioning
yes,
system.
yes, sir. Yes, sir.
Correct?
Actually, I given link to EC WhatsApp group, sir. That's why he joined, I think.
Yeah. Okay, can I remove him?
Okay, sir. Okay, sir.
Okay. A very good afternoon to all. So after a week of gap, we are meeting you, or we are going to start the global positioning system. Right? I think last class was held on 3rd of October. I think so. Then we had a plan to conduct class on 10th, so due to some recruitment or placement activity, it was being off. Last week, all the afternoon sessions were being off due to placement. So we'll start from there. Okay. So I think most probably you would have received all the materials for unit 1, 2, 3, and 4. Right? You can check in your Google Classroom that for all the 1, 2, 3, 4 units, the material has been shared. And next week we'll be having our second internals, which starts from 28 10 2020 and it ends on 31st. So yeah, 28 10 to 31st. So first of all, I would like to inform you about the syllabus for the second internals. The syllabus is unit number 2 and 3. Since we had lesser portion being completed during first internal test, we had only first unit for first internals. For second internals, it is unit 2 and 3. So the pattern is multiple choice question based MCQ type, and the mode of examination will be only in exam.net. So last time you would have done the same format, the same exam.net. Instead of scripting in papers, you need to choose the best answer, or you need to choose the appropriate answers. So that too in the same platform called exam.net. Okay. Unit number 2 and unit number 3 is the syllabus. I'll put it in the type chat box. Second internal. Ocean. Second internal test. Ocean. You can share the same information to your friends, those who are absent for this session, and those who are taking some recruitment drives. Unit 2 and Unit 3 only. Type, type of exam, MCQ type, software or tool to be used. This exam got. So this is an important information regarding your elective threes second internal portion and its type and what is the software to be used. Okay. So now let us move on to the unit number 5. Okay. So this unit number 5 deals with the application of GPS, global positioning system. So to start with the first application, we'll move on to the gravity field mapping. So for the presentation, so GPS based gravity field mapping is the first application where we are going to use this GPS. So the outline of this presentation consists of gravity, geopotential and heights, gravity field spectrum, satellite geodesy, gravity recovery and climate experiment, which we call GRACE in short, gravity field and steady state ocean circulation explorer or GOES, and after that the satellite to surface gravity observations, which can be done by surface gravity or absolute gravity meters. After that we are going to see the effects of terrain or the short wavelength gravity field in terms of residual terrain model RTM, terrain corrections, altimetry analog mesh, point estimates of geoid height or the GNSS leveling, earth gravity models. So finally we'll have a conclusion of this presentation. So what is this gravity? Gravity is that a mass that attracts the other mass, which is given by the constant G is equal to G m1 m2 by r square. So if the mass of the body, mass of the earth, which is always very much greater than the other masses, so then the equation can be given as gravity G is equal to Gm divided by r square. Considering that the mass of another body is very much smaller, so I hide it in small m. Okay. So what is geopotential? So geopotential is that the measurement of the surface of the earth, measurement of surface of the earth within some kilometers or within some meters. So if earth is present below the earth surface or above the earth surface, we will do some measurements depending upon the application. Okay. If you want to find what is the amount of temperature is being present at Delhi, you can sit here and do. If you want to measure how much rain is falling in Hyderabad, you can sit in your place and do. So all is being done with the help of your sensors. So geopotential sensors are being used. So we have different relationships. This gravity is equal to d omega, so dw divided by dr in terms of geopotential. Next is that Earth is more squashed, geodetic, and it is not geocentric. So then how to use h in terms of heights is g is equal to differentiation of W divided by differential H with respect to height. So then we can pick a datum transformation in terms of 1D, one dimensional, two dimensional, or three dimensional as we have seen in unit number 2. So limit varies from 0 to P, G d of n is equal to W naught minus WP, which is equal to CP. So the physical heights relate to the change in geopotential that can be obtained by change of this del Cp. So we can give it as del of C b minus a, which is the change. A is your initial point, B is your ending point. So summation A to B height with respect to its gravity. So how do we find? Is that, for example, assume that we are having a gravity on a geode at station 1, and we are going to measure at the same station surface gravity. And at station 2, we are having G2 as your gravity on geodate and G2 star as surface gravity. And I assume that the height of the station 1 is H1 and the height of the station 2 is H2. So we can find G1 underscore, which is the average gravity from G1 to G1 dash. So you can see that there are 6 representations: C0, C1, C2, C3, C4, C5. I have a station which is being pointed with respect to height H1, another station with respect to height H2. So those are being present. So the surface variations along the Earth's surface, the variations of temperature, the variations of sensing, the variations of water, the movement of water, the water body condition, all can be monitored using this geodate. Okay. So for example, I take the movement of the air. So air is going in this way. So station 1, station 2. So then we can find the average gravity from G1 to G1 star. We can get similarly we can get it for G2 also, which is the average gravity from G2 to G2 star, where G1 is always greater than G2, G1 star is always greater than G2 star, G1, which is the average gravity from G1 to G2 dash, is greater than G2. Similarly, H1, which is the orthometric height of station, is less than the orthometric height of station 2. You can see from the diagram itself. So height. But in the cases that we are going to consider, the Earth is always very big. It is best to move the moist signal. We need to find a good model for determining this, which is GRS 80, which best fits of about 99 percentage. So we need to work with the residual values. So which is residual is equal to actual minus model. What is the actual value minus the modeled value? We get the residual values. So then disturbing potential, which occurs on the measurement, and we do when you do georadical measurements. T is equal to WP minus VP. The gravity anomalies del G is equal to GP minus gamma Q, which is D of T divided by D of H minus 2D by H. We are going to use the Bruns formula, height relationship, Stokes formula, n is equal to R divided by 4 pi G, which is gravity, integral with respect to sigma, del G into S of phi into D sigma. So a simplistic value of S of phi is given by 1 divided by sine of phi by 2 minus 6 sine phi by 2 plus 1 minus 5 sine minus 5 cos phi minus 3 cos ln of sine phi by 2 plus sine square phi by 2. So for every measurements that we do, we need to have a reference. So the since our Earth is in elliptical shaped structure, where when we launch a satellite from the Earth's surface to the moon or to the space, it goes in it follows an elliptical path. So the reference will be always ellipsoid. So this figure is taken from the Haskell and Waters during the year 1967, which is measurement of physical geodesy. Next is the gravity field spectrum. The gravity field spectrum concepts consists of the longer wavelengths, which are being determined by satellites, and the shorter wavelengths, which are determined by terrains. We have the degree spectrum plot, which has the satellite gravity model, aerogravity, surface gravity observations, and the terrain model gravity. You can see what is this long wavelength mean. I'll show you the beginning. I have a mountain. I have a mountain. I have the Earth surface. Longer wavelength. You can see from the graphics. I just press the down button. You can see how it goes off. The satellite is there. Satellite orbit. We have an observed gravity anomalies. The satellite is usually placed about some hundreds of kilometers from the Earth's surface. Then we have different types of structures on the Earth. So the longer wavelength will be as such. So for the particular object, the wave will go like this. In satellite orbit and in observation gravity anomalies. Dealing with the residuals, if the residuals are present, we need to go for gravity anomalies, where del G is equal to Gp minus gamma Q, which is having more signal removed by gamma factor, which accounts for 2 degrees and leaves everything else. So the satellite models are helpful when the satellites are being present up greater than 200 kilometers. The terrestrial gravity coverage are not likely sufficient, so it must use DTM or DEMs. We'll see the DTM or DEMs. So the residual terrain model, which deals with mountains, models the terrain in SHM or EHM, which was used in EGM 2008 and even in SR TM3 to get 3 inch to 5 inch variations. So this could give us a resolution up to 90 meter. So the signal greater than less than 3 affects the gravity values. So we have terrain corrections also, which we use Stokes approach for that, and this removes the gravity observations, and then we can make the geodet model useful. So this is your SHM or EHM model. You can see ellipsoid, two oscillators in circle. The Earth is rotating at the speed of 40,000 kilometers, and you can see the D value at 360 degree 360 is 1 360th of that. I'm showing you the satellite models which are used in orange color, grays or GOCE, airborne and the surface gravity, terrain and density models. You can see how much at what distance or how much is the variance for that. Transition band. So next is the satellite geodesy. The satellite geodesy started with the tracking satellites in the orbits in 1960s. The first dedicated gravity mission was the CHAMP mission that we had seen in Unit 4. And later, Grace was the next in queue. Then GOC was flying within 20 months of that. So likely grace 2 or G/GFO and follow on the ESA missions are being carried out for performing geodesy applications. So the best approach that involved was GNSS receivers with the high-low or low-high tracking in grace. The basic idea was that orbital changes arise from the gravity changes, and we should keep in mind that the gravity is observed in orbit, not on the ground. Also, the orbital height is a function of the sensitivity to scale of functions, which is called as attenuation. So this is an example of the gravity recovery and climate experiment GRACE, which is being used. You can have a look over that. You can see the gravity recovery and climate experiment which was performed for the Earth's surface. You can see the regions. It was discovered by the NASA with a resolution of up to 120 degree. We had dual satellites for orbital tracking at 350 kilometers, and the information was shared from satellite to satellite with low to low and high to low. So solutions gave that the different parts of the world how it is being looking from the uh, space. How does it look? So for further reference, you can see that tsa.u texas.edu/grace. That you can see the gravity field which is being measured at milligauss, so which varies from zero. Zero is the center. So you can have, if you see that, it is minus. Okay, you can see in terms of -10, -20, -30, -40, where it is blue color towards blue. So if you see it is 10, 20, 30, 40, 50, it is towards red. So you can see the fields of attraction, how it is being measured. So which was an uh, measurement being done for exclusively for measuring the climate changes over the earth. So gravity field and steady ocean circulation explorer explored the oceanic and the sea levels, how it is being present, in what manner it is there. You can see the presence of level of sea. If it is if it is fully blue, it indicates that it is depth. Okay, it is very depth. If you see red color shows that it is very height. So this shows that this gravity field and steady state ocean circulation explorer GOCE meant for mainly finding the water level content or the drinking level whichever is being present on the earth's surface. So this determined gradient which was used to integrate del G to surface. Orbital tracking was done about 26 to 60 kilometers. The satellite was very compact and heavy. It had a short life expectancy of 20 minutes. So it resolves gravity with a gravity to D.150 now. Ultimately, it will go to D.200 plus. So you can see that the tallest or the highest peak in the world is present in which is your Mount Everest. So you can see that in that region of in between India and China, you can see that the sea level or the gravity is being very high. You can see 70. Okay. Gravity field measurements. So from satellite to surface gravity observations, the gravimeter type, the surface gravity observations, which was done by the United States data sets of coverage gaps, systemic errors, inter-survey errors were being found. So the surface gravity had absolute errors where the investment of 500 US dollar or more was done, which was done for terrestrial only and national and international gravity networks. In relative meters, this varied for about 100 100k US dollars to 1000k US dollars, which had a pendulum springs with proof mass, surface gravities, terrestrial, shipborne, airborne, satellite, and most of them yielded gravity between them, gravity point measurements. So the absolute gravity meters are a drop of proof mass. So interferometry of fringes were used for checking acceleration. These used to establish control for relative surveys, which had useful for requiring extreme accuracy. So the manufacturers included Micro G Lactose by USA and some other academic and research developments were also being done by absolute gravity meters. So this represents how the model of the absolute gravity meter looks, which is derived from the micro G acoustic. So FGL model meter, A10 model meter, FG5X model meter, all these three. The first left hand side is your FGL, center is your A10, the last one is your FG5X. So the different variation of temperatures, whether it operates in AC or DC is being indicated. If it is into mark, it shows that it is not applicable for that. Okay, the outdoor operation, only the A10 is used for outdoor operation. It has accuracy of about 10 FGL 10, precision 100, repeatability 10, temperature in 15 to 30 degrees Celsius. So the A10 will have accuracy of 10, precision of 100, repeatability of 10, but you can see the temperature is that the temperature varies from -18 to +38 degrees Celsius. So which is which, uh, which can be used on AC and DC also. So next is the relative gravity meters from micro G lactose. So the land meters, lactose is the first. You see, the first blue color display is your lactose rhomber with the index CG, which is used for relative gravity measurements. So in terms of land measurements. So in terms of air measurements, the air or sea gravity system 2, which is this second diagram, is being used for measuring air and sea level. And this is the turnkey airborne gravity system, which is the third diagram, and the system 6 dynamic gravity meter measures the gravity is the fourth diagram. You can see this information of microplastic from this reference. So the surface gravity surveyors are divided into two. One is terrestrial, another one shipborne. So terrestrial is on the land, shipborne is on the sea. So many different sources are being used. Uncertain corrections are there. Potential for bias is big. Individual surveys are generally smaller than the static level. Better distribution generally. The equipment used is portable G meters, GPS or scaled from map. In shipborne, usually fewer sources are used, more corrections are required. Internal consistency may be a problem or a drift. Blown based ice can create huge systematic effect. Greater sampling along tracking. So the equipment uses the bell meter or an air or C2 or GPS or ILB. So these are some of the examples. Existing Gulf Coast gravity holdings where you can see at the seashore nearly 2200 km gravity gaps along the coast are being present, and this is taken at the New Orleans. So this is your space. So in terms of latitude and longitude, the terrestrial gravity, you can see that how it is. This is these graphs. So these are the arrow marks where it indicates. So gravity gaps you can see this region, this region, this region along the coast. So the number of gravity points per 1 cross 1 minute cell, it is being divided in this form. I think this is done for USA, United States of America. The differentiation, all the US is being divided in terms of lines. The borders are lines. So in the same, it is being divided. You can see that the ranges vary from this blue color indicates 1, and if it is red, it is 7. You can see the minimum value is your 1. The maximum value can extend up to 576. So the standard deviation is 2.12, mean 1.55. You can see how the gravity is being present. It is, if this shows in here it is green. Okay, in this whole blue here something is green. So this represents it is an island. You can see these are, since it is being plain, it is water, ocean. So the effect of the terrain on the short wavelength gravity field can be obtained by the DTM or DET or DEM model. So where Earth model is desirable, consistency is important, sample interval varies, LIDAR is the best, but coverage is important at national scale. There are NED or CED differences. Satellites give near global coverage but have gaps. So the examples are SRTM3 or Aster. In DDM, the less significant than DEMs. Del P rock R should be greater than the value of del P rock bar rock. The biggest impact is the shorter wavelength. Satellites capture longer wavelengths. Most geodetic models use uniform density, which is rho. So the DDM would provide better lateral vertical variation. So next is the residual terrain model. So the general concept is that the models, this residual gravity model is applied to gravity field model to remove the effects of the variations in terrain. So EGM 2008 has 5 global issues, which must be accounted for more than uh, 5,000 points for noisy models. So this has to develop a residual RTM. So approximately 3 inch to 5 inch RTM effects are occurring from interpolate of 5 to 3 points. So I'll show you that how it occurs for 5 point. With this, this is the variation. This is for your 3 points. So red is your 5, and the dark red is 3. So again 3 is to 5 is this. Whereas 5 is to 3 is that. So in terrain corrections, the general concept is that the modeling of the terrain on gravity observations, and always this correction should be in positive. The mountain will pull the gravity vector towards it. You can see the mountain here. So the center is your mountain. It will pull to the mountain will pull the gravity vector towards it. The canyon will deflect gravity vector away from it. Net effects of both is reduced to observe the gravity. So applications are that smoothens the gravity field for helmet condensation. Next is the ultimate anomalies, so where missions, the missions of that are GeoSat, ERS-1, BIRD-2, Topics, BIRD, Poseidon, Jason, IceSat, NVSat, Altica, considerations are radar signal or footprint, orbit uncertainties, maximum latitude, track spacing, ice or water returns, Danish products, other products are SIO, GSF, gravity from an altimeter. The biggest assumption is that the MSSH can be used to estimate deltas. MSSH is equal to GOD plus MODT. So the MODT uncertainty is shown in the diagram. So ocean is below, and it is ocean bottom. So the geodetic surface. The littoral regions fully are known for a depth of about 500 meters, which may help in retracking MSSH and MODT. You can see the diagram. MODT uncertainty model, MODT model. Actual MODT predict the GOD that derived deltas are likewise in error, and you can find gravity from that ultimeter. So the altimeter profiles you can see for an Mediterranean occidental. So we have latitude and longitude. So the tropics Poseidon are being indicated in light orange, and Jason in red, GFO in blue, in green, in the sat. So these are the different altimeter positioning that has been determined for the measurement of gravities. So image from the center of topograph of the oceans and the hydrosphere can be obtained from the CTOH. So they measure the hydrospheric profiles, making a note that the satellites orbits vary a lot, with SRTM having only crowd of plus or minus 60, where most are sun synchronous, having an 117 inclination, which is approximately plus or minus 83. So you can see the free air gravity analogous from satellite altimeter, which is taken from the reference Anderson in the year 2010. You can see the variations of gravity, free air gravity, how it is being moving from one place to another place throughout the universe. And this is a physical representation of the globe structure also. The top end right side we have India. Then when moving towards left side we get Saudi Arabia, Africa continent. We have the European at the top, and at center or at the middle we have the South America, and at the top we have the North America, and at last we have the China and Japan, followed by Australia, China, and so gravity field measured from the double retracting satellite element. So ground affects maximum fitment. The aerogravity spans the other two, determined by the extent of survey. So the other benefits of aerogravity is that it can span a greater territory than surface gravity. It can connect different observation environmentals, terrestrial to shipborne to altimetry, can be fixed to satellite model gravity at longer wavelength. It can fix the systematic errors in surface surveys. can be used in equipments, techniques, software, and procedures that are already established and being refined for aerogravity. The point estimates of the GOD, the height, or GNSS are leveling. So this is ultimately the desired product. However, these data will be sparse and irregular. Care must be taken if these are combined in a single least squares adjustment with other functions of the gravity field. Systematic effects must be guarded against them. So the Earth gravity models are found by the NIMA in EGM 1996. The problems in longer wavelength with having no grace or GOC data was being done, which had to melt terrestrial solution with deep 0.72. So there would be a good through the degree 360-degree was being done for 111 kilometer resolutions. For EGM 2008, it was done in 2008, produced by the NGA, which had more refined resolutions, including grace, good through degree 2160 of having a 11 kilometer resolution. So the modeling is innovation by the EHM coefficients. The harmonics are increasing. The harmonics these ones. Applying a weight to these functions increases or decreases their power. When added, the harmonics uh, match the unique shape of the Earth's gravity field. The trick is to solve for the weights with the gravity observations and the functions. No. The EGM 2008 model is this. We have A values, which is the semi-major axis of ellipsoid, A, which are GOD the undulation values with respect to wide area drone fusion system. You can see the NGA geoscience division has performed this. So where blue is your 10 minus 107 and whereas red is your 56. You can see geodetic heights with respect to that. Okay. So tide free system, NGA developing a wide GPS system of 84, nominally 5-inch or 11-kilometer model is being dealt in, so where data is in some regions is 15, the nominal is 5. So grids are available, can also get the EHF coefficient. So you can refer this in this link earth.info.nga.mil GNG WGS gravity model EGM 2008. So the GM value which we are talking about is the product of the Earth's mass and the gravitational constant, which is approximately 3.98600418 Newton per 14 meters cube per second square. And the Earth's angular velocity is approximately omega is equal to 73 into 10 power minus 11 radians per second. In regional modeling, the general approach is to start from an EGM and refine using remove, capture, restore technique, where the gravity observations from multiple sources, terrestrial, shipborne, airborne, and altimetry, are being used. Note that a lot of this same data went into EGM 2008, and this must adapt an approach which uses helmet and the mono density depending upon application you to choose, which is being best. So this accounts for terrain using RTM or TC that yields localized gravimetric geodic height model. And what is this molodensity and helmet model is that molodensity key is relevant to height anomalies, whereas helmet is geodid heights. And the helmet follow geodid approximates MSL. This molodensity uses a telluride, follows terrain, which has surface gravity, and these are downward continue to MSL. These has no assumptions about rho. These has assumptions to geodid with rho. This is the Russian approach from 1960s. This is the traditional approach. This is much more rigorous theory. These are having lots of assumptions required. Inversion is very rough. We are more rigorous with advanced computing, popular in flatter countries, more consistent across mountains, normal heights, and this is helmet automatic height. So the conclusion is that the gravity, geopotential, DOVs are heights and are related functions of the Earth's gravity field. So in many instances, obtaining one type of data is sufficient for resolving all the others. Hence, collecting gravity from space on a plane or in an aircraft can help determine the heights on the ground. So the long wavelengths are best resolved by using satellites, this which provide a global consistency for all models. Grace and ghosts will likely resolve gravity field degree to of about 200 to 200 kilometers per meter scaled features. So the terrestrial gravity can have systematic features that create a decibel to meter level errors in the geoid, where the effects of the terrain must be taken into account or risk making data look noisy. So the aerogravity point provides a mean provides a bridge between the gap of surface gravity and satellite gravity. Aerogravity's function is that so the aerogravity can span across different environments, land and ocean. So this can provide a seamless connection through gravity field across a continent and through middle of the gravity spectrum. So the DOVs can be derived from observed data and yield better control for IMUs where each gravity model such as EGM 2008 use all available data for comprehensive reference model. So the adaptation of gravimetric geoids is the best means of improving accuracy of national vertical data, which is from the Earth surface to the satellite or to the space. So that is your vertical. Using a globally accepted reference field will be best ensured to get the information about the world height system. Next is the regional geodetic modeling that provide local refinements with goal of centimeter level accuracy. The regional models can be built from EGMs. These models provide the basics for comparison to national vertical data that involve procedures to fit regional gravimetric geoids through control ideas. This hybrid process keeps the character of the geoid between points while fitting the data. References for my presentation is Lange RB, why is the GPS so complex, the GPS world, Wayne Hoffman, Wayne Hoff, H. Ginger and J. Collins, GPS theory and practice, Hellenic GPS, satellite surveying, John Willison, Wells D. et al. Guide to GPS Commissioning, Supplementary Understanding GPS Principles and Applications, Shaw M. K. Sandhu and Turner, Modernization of the Global Positioning System, Lange RB, the Mathematics of GPS, only RF Light, Auto Selective Availability, C. Parkinson, J. Springer Jr., GPS Theory and Applications, A. Klunsberg and C. Swinsing, GPS for Geodesy, Ahmed L. Rabani, Introduction to GPS, the Global Positioning System. GPS for Dummies by Joel McNamara, 2008. Understanding GPS Principles to Groner's website, official Galileo homepage website, Ice Shelf Tidal Animations website. For, for any queries, you can type in the chat box. Since there are no queries for the presentation on gravity field, we'll move on to the next topic, which is meteorology, meteorology for climatic applications. How this GPS is used as a meteorology measurement for climatic applications. So the detection of climate changes, the uncertainty of the IWV, the uncertainty due to short-term variation in IWV, the evaluation of climate models, how those are being useful. We'll see that. So to start with the detection of climate changes, the long-term measurement of the integrated water vapor is what IWV stands for. So the integrated water vapor which is being present in the atmosphere is to be measured. So which can be done by some traditional approaches. So we had used radio sounds for a longer time during 1992 to 1996 and further 2001. So the traditional radio sounds are used for climate research that determines the integrated water vapor content in the atmosphere, such that we can predict whether is there any global warming scenarios for the future. So the limitation of this radio sound data for climate research is that the derived IWV is not homogeneous over long time periods due to calibration uncertainties and sensor changes. So they used a WVR that can use to provide IWV estimates was done by researcher Elgwed and Jacmal Mark in 1998. However, the WVR technique has not been proven to be sufficiently stable in terms of determining the long-term series of IWV. So furthermore, the WVR is not a commonly used instrument and it is inaccurate when drop size is not significantly smaller than the observed wavelength during rains. So the poor temporal and spatial resolutions of the VI derived IWV limit had the role of VLB technique for climatic applications such that they are being used as an external data source for validation at specific locations where it can be extremely useful. So working under in principle all weather conditions with increasing spatial resolution locally and globally, the GPS technique seems to be superior that provides a stable long-time series of the IWV compared to the other techniques mentioned. You can see and there are two graphs being done. One is at Sorry, I had an important call, so I was I made a mute of the mic. So the linear trends of the integrated water vapor time series can be obtained by using a model which considers the seasonal variations in the IWV. For a GPS data set, the components, the components needed to describe the seasonal variations has been investigated by the method of long scale periodograms by Hosky 1998. Two examples are shown in the figure I'll show you, which is REYK, which is located at minus 18.96 degree east and being positioned at latitude of 64.14 degree north, and at BRAZ, which we had seen in the diagram, minus 47.88 degree east and minus 15.95 degree north. So the results indicated that the most marked integrated water vapor variations are at frequencies centering on the annual and semi-annual terms. The diurnal and the semi-diurnal, however, have much smaller amplitudes, causing insignificant impact on the resulting trend. So therefore, it is sufficient to use an annual and semi-annual term to describe the seasonal variations in the IWV. The model used for the trend estimations is expressed as below, which is y is equal to y naught plus a1t plus a2 sine of 2 pi t plus a3 cos 2 pi t plus a4 sine 4 pi t plus a5 cos 4 pi t, where y is the integrated water vapor and t is the timing years. The parameters y naught and a1 are the mean coefficient, offset, and the linear trend of IWV respectively. A2, A3 are the annual component coefficient, A4, A5 are the semi-annual component coefficients. Yes, yeah. The IWV trends for 42 globally distributed GPS sites, which were estimated using 15 years of data from the NCR Global. The two examples of the IWV time series, together with the fitted seasonal components and the linear trends, is shown in the REYK and BRAZ. It is evident that the model fits seasonal pattern of the IWV well, while there are short-term variations with a time scale of few weeks or less, which are not described by the model. Now the examples of time series of IWV for REYK and BRAZ, which is shown here. So this is the diagram for that throughout the year from 1996 to 2012. The variations are being noted, which is green color represents the IWV, blue is the seasonal, and red is the PREF. Display for linear trends and seasonal components. So this is the 42 global GPS sites for the time period from 1997 to December 2011 is being obtained. So green, the blue, orange are the spots. The blue represents negative trends. The red circle means positive trends. The uncertainty of the estimated IWD trend is that it is being decided by many factors: the time span of available data, magnitude of variability, and the autocorrelation of the noise. Correspondingly, the uncertain of our estimated IWV trend is determined by the length of the IWV time series, the magnitude of the uncertainty of the individual GPS derived IWV, and the short-term variations in the IWV. The Weatherhead et al. 1998 also pointed out that the detection of the true trend can be difficult when sudden changes occur in the data, such as when an instrument is changed. This could also happen to our GPS dataset due to antenna or random changes or an implementation of microwave absorbing material. The uncertainty due to the short-term variation in IWV can be modeled by the quantity x square is equal to summation I is equal to 1 to n vi minus vi whole cap the whole square by sigma I square, where n is the number of data points vi and sigma I are the GPS derived IWV and the corresponding uncertainty respectively. If the model fits the IWV time series adequately, the variance of the residuals should agree well with the uncertainty of the GPS derived integrated water vapor structure, and it should be around 1. The covariance of the residuals after the model fit for the two GPS sites is shown here. A is REYK and B is BREZ. So the ratio can be estimated by the reduced chi-square error method, where V is the number of degrees of freedom usually given by n capital N minus 1, and n is the number of unknown coefficients. For simplification, a common value of 0.76 km per meter square is being used as the uncertainty for all IWV estimates and for all signs. The reduced chi-square values significantly deviate from 1, varying from 4 to 196, and tend to increase with decreasing absolute latitude. So this implies that the residuals after the model fit are actually not white noise, due to the fact that the true short-term variability in the IWV is not modeled. Therefore, residuals are correlated over several days. Two examples of such are correlated in the figure as shown, where covariances calculated from the residuals are being model fit for demonstration for REYK and BREZ. A long decorrelation time was seen for the BREZ site, which is located at lower latitude, so that the calculation of the trend uncertainty after taking these short-term variations are into account. A model that can describe the covariance between IWV values V1 and V2 observed at the time epochs T1 and T2 was used. So this is the uncertainties after taking short-term variations into account. So if it is blue, it is nearly 0.23 or 0.2. So if it is orange, you can see it is orange is around 1.6, and if it is green, it is 1, and if it is lightish blue, it is 0.6 when it goes on. Uncertainties of the IWV trends. In order to obtain the coefficients A1, A2, T1, T2, the covariance of the residuals fit after the IWV to the model was first calculated. Then these were used in a nonlinear least square fit to obtain all the coefficients from the covariance model. So the covariance matrix can be used for computing uncertainties. So C error is equal to X transpose X the whole inverse X transpose C X transpose X the whole inverse, where X is the design matrix and the C error is the covariance matrix for the uncertainties of the estimated parameter. So the resulting trend uncertainties for all 42 GPS sites was shown, which had an uncertainties varying in the interval 0.21 to 1.5 kilogram per meter square decade, and large values observed at latitude was approximately in the regions of minus 30 degree north to plus 30 degree north. So the ratio of the estimated IW trends and corresponding trend uncertainties was found that most of the trends are insignificant given the magnitude of uncertainty. The impact of uncertainty in the individual estimate on the resulting can be approximated using the error covariance matrix, assuming that after the residuals, the model fit are described by white noise. If still the set of common value of the integrated water vapor would be 0.76 kilogram per meter square, which was much smaller than the trend uncertainties of taking short-term variations of IWV into account. A complication in the IWV trend estimation is that changes during the operation of a GPS site may also cause systematic effects in the IWV time series, which may change the resulting trend. For example, a GPS site which is present at ONSA, ONSA Space Laboratory, had a random change on 1 February 1999, which introduced an offset in the IWV time series. So the magnitude of the offset can be determined from the IWV comparison between the GPS data and the one acquired from a co-located technique which is homogeneous. For the answer side, this was done by comparing the GPS derived IWV to the IW estimated from the VLBI data which were acquired 78 meters away from the GPS site. So an important is that the signal path also causes systematic errors in the GPS derived where multipath effects are not fixed in time as they are very much sensitive to the surrounding environment that reflect properties. It was given by Grandstrom and Johnson in the year 2005. So the multipath impact is larger for observations at low elevation angles, which are included in the order to improve the geometry and reduce the formal error of individual IWV estimate. Therefore, higher elevation cutoff angles are desired for the IWV trend estimation due to the fact that the formal error of the IWV has much smaller impact on the resulting trend due to the relative short-term period of the GPS derived IWV. The short-term variations in the IWV dominate the uncertainty of the estimated linear trends. It should also be pointed out that the impact from the systematic error due to the specific range related to an instrumental cannot be ignored. Next is an important concept of evaluation of climate models. So before that, I'll show you the model where this is being occurring. You can see with latitude and longitude values, I'll show that uncertainty of estimated. So the next is evaluation of climate models. The Earth's climate system involves a variety of processes operating on different temporal and spatial scales, where the global simulations of the most of these processes are given by global climate models that are able to simulate the climate system, including its change over time. So the simulations for the past and present are of great importance for us to understand the Earth's climate system and causes for the climate change. So these are also used to stimulate the response of the climate system to current and future changes in radiative forcing, given by Mehel et al. In 2007. So the increase of the greenhouse gases was being monitored. So these responses are normally referred to as climate feedbacks based on the comparison of the global climate feedback process for several GCMs. Boni et al. In 2006 found out that the water vapor feedback is most important climate feedback. In addition, as discussed, the movement of water vapor through the hydrological cycle is strongly coupled to precipitation and soil moisture and redistributes energy. The vital role of water vapor in the climate system requires that climate models can represent this atmospheric process for different spatial resolutions, from scales of micrometers up to thousands of kilometers. So typically, a GCM operates on a spatial resolution of 100 to 300 kilometers. In order to obtain a finer spatial resolution, the local climate is often simulated using regional climate models, which operates on a horizontal resolution, typically from 10 to 50 km. Running with appropriate boundary conditions, RCMs have been shown to reproduce many important features of regional or local climate. Over the Western Arctic Ocean, the evolution of 8 RCMs using the same boundary conditions was done. They found that vertically integrated water vapor are reasonably well simulated at monthly and daily timescales, but considerably differences between individual models. The Rosby Central Atmospheric Climate Model is developed at the Swedish Meteorological and Hydrological Institute in order to provide regional climate scenarios. This RCA model versions have been run using the European Centre for Medium Range Weather Forecasts (ECMWF) reanalysis data as boundary conditions. The RCA simulation will differ from the ECMWF reanalysis due to the data assimilation done in this forecasting, which keeps the model closer to the observations. Meanwhile, the stability of the IWV time series from ECMWF data is limited due to the changes in the observing systems as given by Bengtson et al. In 2004. Therefore, the evolution of the IWV simulated by climatic models use independent observations of the IWV with high accuracy was done, which gave the ability of operating under almost all weather conditions on the long-term stability. The GPS technique has superiority to measure long-time series of the IWV with temporal resolution as high as few minutes. As GPS receivers are increasing in numbers globally and locally, the spatial resolution of the GPS-derived IWV will also be improved. The uncertainty of the GPS-derived IWV is possible to be known 1 kilogram per meter square. So in addition, the different to the radio zone data, the GPS data have not yet been assimilated in any climate reanalysis products, which makes them an independent data set suitable for the evaluation of climate models. The IWV time series inferred from the ground-based GPS measurements can be used to access climate models in terms of the following aspects. The evaluation of the representation of the IWV in models by comparing the model simulation to the GPS-derived IWV. Using the IWV obtained from GPS networks, one can identify model deficiencies for different weather systems, land and coastal areas. The diurnal cycle is one of the most obvious and reliable signals of the climate. Therefore, given its high temporal resolution, a GPS-derived IWV is designed to evaluate the ability of the climate models to simulate the diurnal cycles of the IWV, where a detailed description of the IWV obtained from the GPS data and RCA simulation result shows a good agreement between the GPS and the model data in terms of diurnal phases. The amplitude for the GPS data varies from 0.05 kg per meter square to 1.48 kg per meter square. The comparison of the GPS derived IWV to the model simulation applying different horizontal resolution can be used to investigate the sensitivity of the model grid point chosen for the IWV representation. The vertical transport of the water vapor is sensitive to the model vertical resolution. Therefore, comparisons to the model simulation run with different vertical resolutions can also provide useful information. The conclusion is that the vital role of water vapor in Earth's climate system requires the measurement of the atmospheric IWV with a long-term stability and a high accuracy. This presentation gives different and methodologies and methods that are being used by some of the techniques in order to infer IWV with the main focus on the GPS. The advantages is that GPS measurement that can be performed independently on weather and having high temporal resolution on the IWV estimates. Meanwhile, along the densification extension of permanent GPS site networks globally and regionally, a continuously improving spatial resolution is required. Therefore, the GPS measurements provide estimates of the IWV above receivers on the ground as a promising application. References for my presentation is Lange RB, why is the GPS network complex in the GPS world? Ben Hoffman, Wellenhoff, H. Wickinger, and J. Collins, GPS theory and practice. Hellenic GPS pattern surveying, John Willison. Wells D. et al. Guide to GPS positioning. Kaplan E. Understanding GPS principles and applications. Shaw M. K. Sandhu and Turner, Modernization of the Global Positioning System. Landry R. B. The Mathematics of GPS. Only RF Life, Authors Selective Availability. B. Parkinson, J. Springer Jr., GPS Theory and Applications. A. Klunsberg and C. Kunsing, GPS for Geodesy. Ahmad L. Rabani, Introduction to GPS, Global Positioning System. GPS for Dummies by Joel McNamara, 2008. Understanding GPS Principles and Applications by Elmer Kaplan and Christopher Negari. Applications of GPS website. Civilian applications of GPS website. GPS World website. A guide to GLONASS website. Official Galileo homepage website. Ice Shelf Tidal Animations website. If you have any questions, you can type in the chat box. Hi everyone, this is T. Dinesh Kumar, established by a variety of national and international organizations to provide DP1. This is T. Dinesh Kumar. In this video, I'm going to explain you about the applications of GPS in geophysics. A continuous global positioning satellite tracks networks are being established by a variety of national and international organizations to provide basic infrastructure for space age navigation
surveying, science, engineering, and atmospheric sensing. The emerging networks present opportunities for a variety of geoscience applications. To make the most of these opportunities, the geoscience community should clarify and communicate its research goals to organizations establishing global positioning networks. GPS having GPS satellites and networks began to establish soon after the space age was deployed. Since it was recognized that the orbits of satellites provided a valuable reference frame for global navigation systems. Today, the 24 satellite GPS operated by the Department of Defense is the most widely used system, followed by a smaller group of Russian satellites called GLONASS. These systems may be augmented by future commercial low Earth orbiting communication and positioning satellite services. The reference frames of satellite orbits and the Earth's crust are linked using ground-based tracking networks. The first global GPS tracking network was established more than 15 years ago by the United States Department of Defense, which included a network having 5 tracking stations, and it was used to determine the orbital positions with an accuracy of about 10 meters. More recently, the International Association of Geodesy IAG established the International GPS Service for Geodynamics, comprising more than 50 international organizations to support geodetic and geophysical GPS applications. Example was given in Zuckerberg et al. In 1994. The IGS network includes more than 50 globally distributed tracking stations that provide high accuracy GPS orbits with approximately 10 centimeter accuracies, allowing users to place their GPS stations in international terrestrial reference frame with centimeter accuracies. The regional continuous GPS networks designed mainly to monitor trains for earthquake research and forecasting have been operated in Japan and California for several years. A similar network in Sweden was designed to measure post-glacial deformation that has operated for more than a year. Similar systems are being established across Europe, Australia, and other regions also. In addition, networks are designed to improve GPS accuracy are being established for aircraft, coastal navigation, to support surveying applications, for dam, dike monitoring, and for atmospheric measurements. The navigation increasingly land, sea, and air vehicles are making increasing use of the capability of GPS to determine point positions with an accuracy of about 100 meters. Positioning with so-called DGPS or the differential GPS, which uses radio links between mobile and fixed GPS receivers, provides relative positions in real time with an accuracy of 10 centimeter to 1 meter for civil aviation and coastal navigation. An example of the use of DGPS is the coordination of highways and railroad traffics that we are using now. In science, high accuracy GPS positioning has been improved by 2 orders of magnitude during the past decade, and now millimeter accuracies are being routinely achieved with this high accuracy makes GPS useful for tectonic, earthquake, geology, and ecology studies. In engineering, surveying, and resource management, the GPS is also being used for surveying, monitoring dams, dikes, landslides, and subdrains, positioning civil infrastructure for use in GIS, time transfer for telecommunication systems, automated construction, facilities management, precise farming, forest, and resource management with natural resource exploration also. In weather forecasting, by exploiting the delays in the GPS signals introduced by water vapor and other components of the atmosphere, GPS networks can provide valuable data for assimilation into numerical weather prediction models. This is just an example of the diagram where the geodynamics can be obtained. So you can see the solid inner core, we have Mandel convention, we have the thermal boundary, we have transition, then we have the lower mantle, then we have the upper mantle, and in the after the upper mantle we have the atmosphere, then we have subduction. So where on all these things we have our environment. So the amount of terrains, the amount of volcanoes, the amount of water bodies, the amount of pollution or whatever might be can be easily monitored by using this application of GPS. So these are the exploration methods. If you want to find land gravity, position horizontal should be 10 and position in vertical should be 0.03 in meters. Suitable methods are DGPS static, L1, L2, rapid static, semi-kinematic, L1 or L1 and L2 for real-time semi-kinematic with horizontal pure kinematic bands for them and the appropriate processing methods. Airborne gravity 100 horizontal positioning, vertical 3 DGPS is being used with real-time pure kinematic and pure kinematic bands. Land seismic horizontal positioning of 5, vertical as 1 DGPS, the static, rapid static, real-time semi-kinematic. Marine seismic activities with horizontal positioning of 5 meters and vertical do not require because it is below the surface of the earth, so or along the surface of the earth. So with DGPS, real-time DGPS, real-time pure kinematic or pure kinematic mechanisms with its appropriate processing and appropriate frequency bands. So we can do ground magnetics with vertical as with a height of 3 meters where horizontal is not required. So DGPS, static, C bar A, course or acquisition can be used, rapid static, intermittent static, semi-kinematic, RTD, GPS. RTD, semi-kinematic with different frequency bands. In aeromagnetics, DGPS of about 15-meter horizontal positioning and 1 meter vertical positioning can be done by using a suitable GPS method of pure kinematic L1, L2 or L1 and L2 and pure kinematic system. General airborne applications can be done with point GPS or DGPS. Real-time pure kinematic or real-time pure kinematic in both the bands. Reconnaissance exploration can be done up to 100 meters of horizontal positioning with point GPS or C bar A methods. General navigation up to 100 meters in horizontal can be done with same point GPS or course bar acquisition as in this table. Then large scale grinding can be done up to 50 to 100 horizontal meter positioning, DGPS, RT, real time and static C bar U. And small scale gridding can be done up to 5 from 5 to 10 meter of horizontal positioning. The DGPS, RTD can be done with static or intermittent static. Detail gridding can be done up to a vertical height of 1 meter with horizontal positioning of 0.1 to 1 meter. So the technology or the method can be adopted as DGPS, RT semi-kinematic on all the frequency bands. Here a detailed expansion of the processing methods. PP represents your post-processing, RT represents your real-time processing, C bar A is your course or acquisition cold storage ranges, where L1 is the carrier phase single phase carrier, L1 and L2 is the dual frequency carrier. The applications of geodesy is that floodplain mapping, which relies on accurate heights and supports the local officials and home owners to locate the floodplains in their area. Boundary determination. It relies on accurate positioning and supports land surveyors as well as GIS analytics and property owners about the boundary of their house, building, or land, whatever they have. In construction, it is used in construction of roads, dams, airports, and ports that relies on accurate positioning too and supports engineers, pilots, and many more. In physical sciences, it relies on accurate geospatial information where study plate tectonics, hydrology, or even more can be done. You can see some of those examples in diagram. Floodplains, boundaries, determining boundaries, construction sites, and in sciences. References for my presentation is Langy RB. Why is the GPS signal so complex? The GPS world. Hoffman, Mellenhoff, H. Ginger, and J. Collins. GPS theory and practice. Alienic GPS.
Any questions or any doubts, you can type in the chat box. If no queries, we'll end up the session. If there are no queries, you can leave the meeting. The attendance is being auto marked. So this session's attendance, I'll put it in our WhatsApp group. You can check the attendance there. A reminder of the second internal test portion and its type and the software, I am putting it in chat box also. So kindly go through.